An engineer is studying early morning traffic patterns at an intersection. The observation period begins at 5:30 a.m. Let X denote the time of arrival of the first vehicle from the north-south direction, and Y is the time of the first arrival from the east-west direction. Time is measured in fractions of an hour after 5:30 a.m. I guess what they mean by that is like 0.1 hours would be 1/10 of an hour, which would be 6 minutes. Assume the density for this bivariate random variable is given by the formula that you see there. That's the joint density. F of xy is 1 over x. You don't see any y in that formula. It's okay. The formula doesn't depend on y, but the domain does. The domain does depend on both x and y, and it's written in kind of a strange way. Makes you think, well, I guess x and y both go between 0 and 1. Yes, but with the caveat that y is always less than x. That notation means y is always less than x. X and y are not arbitrary numbers between 0 and 1. Y has to be less than x. So if you're going to visualize this domain, try to draw it here in the xy plane. X and y are always between 0 and 1. But y is always less than x. In other words, the points you're considering are going to be below the line of slope 1 to the origin, below the line y equals x. They'll have to be in this triangular region right here. Sorry, that seems to be blurring a lot. They'll have to be in that triangular region. It's a non-rectangular domain, a triangular domain. You could describe this as the set of all points, x, y, that satisfy the condition that, just like in the Mathematica document, 0 is less than y, is less than x, is less than 1. The claim is the function f sub xy, indicating that it's a joint PDF, of little x, little y equals 1 over little x, is a PDF over this domain. To verify that, we'd have to integrate it and confirm that it integrates to 1. Integrate this function, 1 over x, with respect to an area element is the way to write it in the abstract, over this domain, called the domain D. But to do that integral, you have to do it as an iterated integral, either with respect to x in the inner integral, and then with respect to y, or vice versa. You could do it either way, but it's kind of tricky. Let's try it with respect to x and the inner integral first, and y for the outer integral. How do you do this? You always want your outer integral to go between two numbers. In this case, y is always definitely between 0 and 1. So y goes from 0 to 1. That's the outer integral. But the inner integral, because this is not a rectangle, is not going to have two constants that are the limits of integration. One of them is in fact going to depend on y. For each y value between 0 and 1, pretend this is a particular y value that you're thinking about. How does x vary for that given y value? It varies from the x coordinate of this point to the x coordinate of that point. Well, the x coordinate of the second point is easy. That's 1. What's the x coordinate of the first point in terms of the specific number y? Go ahead. It's y. This point has coordinates x, y. And for a given value of y, a given fixed value of y, that point is on the line y equals x. And so the x and y coordinates are equal. I could replace the x with y, because you're on that line where the x and y coordinates are equal. the line y equals x. And you do want to do that because the outer integral is with respect to y. You want this inner integral to make the x go away and give you something that just depends on y. You don't want to put an x there, because then when you do the integral, you'll still get an x. Do that inner integral, treat y as a constant when you do the inner integral. Do it with respect to x, you'll get natural log of x, or you might say natural log of the absolute value of x, although x is positive, so you don't really need those absolute value signs there. X goes from y to 1. Now plug in those limits of integration. Get natural log of 1 minus natural log of y. Natural log of 1 is 0. So we need to integrate negative natural log of y. What a weird thing to integrate for a PDF. Is that going to be positive? It is actually going to be positive in spite of the negative sign, because natural log of y, when y is between 0 and 1, is less than or equal to 0. So if I put a negative sign in front of it, I do get a quantity greater than or equal to 0. However, it's still a little tricky. This is actually an improper integral, because natural log of 0 is undefined. Oh boy, is this going to wreck things? Well, let's keep going. It also looks tricky because how do you find the antiderivative of natural log of y? The derivative's easy, right? Derivative of natural log of y is 1 over y. But what's its integral? Anybody have an idea what technique to use here? Let's go ahead and do it by hand. Here's a little hint. Integration by parts. Let u equal natural log of y. So u prime is 1 over y. Or maybe you learned that as du is 1 over y dy. And what's v prime? Or dv if you prefer, to do this integral. Put the negative sign on the front and don't worry about it for the moment. Remember how to do integration by parts? It's just 1, right? You want, if this negative sign comes out in front, you want the integrand to be the product of two functions, one of which you call u and one of which you call v prime. You hope that u prime is simpler than u. Yeah, 1 over y is simpler than natural log of y. And you also hope v prime is something easy to integrate. Well, 1 is easy to integrate. V will be just y. The variable here is y. If you're used to using dv, dv would equal dy. Integrate that, v will equal y. So the integration by parts formula would tell you that this is negative. I probably should use a limit sign in here as well. The limit, as the lower limit of integration, a, call it, goes to 0 from the right. How does integration by parts go? It's u times v. Multiply those two things, y and natural log of y. Limits of integration would be a to 1 minus the integral of v times u prime. Hey, the product of those two things is simple, 1. That also goes from a to 1. Looks kind of complicated. You can do it. Well, maybe not without technology to help. You might wonder, does this limit even exist here? Let's keep the negative sign out in front there. Limit as a goes to 0 from the right. Plug in y equals 1, you get 1 times natural log of 1, which is 0. Plug in y equals a, you get a times natural log of a. And you might wonder, does that limit exist even? After all, natural log of a goes to minus infinity as a goes to 0, right? You know that. Graph of natural log goes down forever and ever. However, if we multiply it by a, which goes to 0 as a goes to 0, it turns out this product goes to 0. This goes to 0. And you can check that with your calculator. You could graph x times natural log of x near x equals 0 and see it goes to 0. So now you're left with negative of the limit as a goes to 0 from the right of lots of negative signs here. 1 minus a with a negative sign in front of it. Those two negative signs cancel. You end up with 1 minus 0 when you plug in a equals 0 and you get 1. That was a lot of work to confirm it's a PDF. I did this integral with respect to x first, then y. Could I have done it the other way around? Yes. Will it be just as much work? I think the other way around is a lot easier. Let's try it that way. So what I did up here was I did the inner integral with respect to x and then the outer integral with respect to y. Let's try it the other way around. Let's try the inner integral with respect to y and the outer integral with respect to x. Once again, when you do these integrals over a non-rectangular region, you do want the outer limits of integration for the outer integral to be numbers. X goes from 0 to 1, just like y did. X goes from 0 to 1. That's still the outer limits of the integral, of the outer integral. But what about the inner integral with respect to y? Go back up here and think in the same kind of way. For a given value of x, pretend it's right there. Pretend that's fixed. How does y vary? It varies from the first coordinate of this point, the second coordinate of this point, which is 0, to the second coordinate of this point, which is y, but it's also on the line y equals x, so it actually also equals x. And you want to use x for that upper limit of integration because you want to get rid of y. You don't want to put a y there because then you won't get rid of the y. And yeah, I believe this is going to be easier to do. First, integrate with respect to y. Treat x as a constant initially. So 1 over x is a constant. Integrate 1 over x with respect to y, you get 1 over x times y. Y goes from 0 to x. I just did the inner integral there. Replace y with x. 1 over x times x is just 1. Replace y with 0, you get 0. Hey, this is nothing more than the integral from 0 to 1 of 1, which is obviously 1. Done. That integral is a lot easier to do. How about that? That sometimes happens. So if I give you a problem, and I'm not sure if I will, I know there's a non-rectangular problem for the homework due next time. No, it's not. It's easier than this one. If I put one similar to this on the test, probably I'd have to tell you which way to do it to make it easier, because otherwise you're just experimenting. It's just trial and error. But that's a general lesson about double integrals like this, is sometimes the integral is easier to do one way than the other way. So it's a good problem-solving tool to realize that. So it is a valid PDF. What does this graph look like? How can we think about it intuitively? We are also ultimately going to find some things. We'll find conditional densities in a curve of regression and the mean value of x when y is 0.5, kind of like on the exam problem you had with the rectangular domain. So here's a picture of the graph of the PDF, a partial graph. It actually goes up forever and ever. It's got a vertical asymptote here. The x-axis goes to the right. The y-axis goes into the screen. Z-axis, the outputs, go upwards. This is the graph of 1 over x for all x and y in this triangular region. The triangular region is in the xy plane looking straight down in this graph. That's the domain effectively. But now when I look at it this way, I'm seeing the z coordinates. 1 over x. They only depend on x. So for any fixed value of x, say right here, it doesn't matter what y is. You see all the outputs along that line where x is fixed are the same. Same along here, same along here, same along here. you look at it head on, it looks like it's just a curve. It looks like 1 over x. It's the volume of the region of the solid underneath that graph that equals 1. That makes this a PDF. And that does equal 1 in spite of the fact that there's a vertical asymptote here as x approaches 0. It's not the only way to visualize this. You can also visualize it with a contour plot. Contour plot. Shows you level curves of the function, though not very many here. Let me add more. And it's not showing as much as the graph as you might like here because you're heading off toward the vertical asymptote over here. These lines are the level curves. Along these lines, the function output is constant. This particular line is close to x equals 0.4. Notice, I don't know if you can see that number there. The output says 2.53. 1 over 0.4 is 2.5. We're slightly to the left of 0.4 there. This next output is a little higher, 2.64, etc. This one's 3.96. Thinking intuitively about probability, most of the probability is down here where the function is output, where the density is higher. That's where most of the volume under the graph is. So if you can simulate data from this distribution, most of the points should be low in value for x and y. I can simulate it here. Yeah, Mathematica can confirm the PDF does integrate to 1. What are the marginal PDFs? Let's try to do one of the marginal PDFs by hand. Well, we actually already did them effectively. That thing right there, which simplifies to this, is the marginal PDF for y. We integrated out the x. And one is the marginal PDF for x. Let's be careful here. Let's be a little bit more formal. What's the marginal PDF for y? We have to integrate out the x. And just like before, for any fixed value of y, think about this horizontal line, x goes between the first coordinate of this point and the first coordinate of this point. Y to 1. You don't want the result to depend on y in general. That ends up being this. Oh, I forgot it. Yeah, we are going to get a minus sign in there. This becomes natural log of 1 minus natural log of y, and that simplifies to negative natural log of y. Y going between 0 and 1. Natural log of 1 is 0. Marginal PDF of x. Integrate the joint PDF with respect to y. And just like before, y goes from 0 to x. And just like before, this simplifies to just 1. For x between 0 and 1. What are we after here in this problem? Well, we were partially after those marginal PDFs. So that we can find these conditional densities and ultimately the curve of regression, the curves of regression. What's the conditional density of X given Y? Okay, this is good to review. When you think about this particular conditional density, in your mind, you want to imagine Y is fixed. You're pretending you know what little y is. And you're wondering about the resulting behavior of the variable X. Meaning this is really ultimately a function of X. Recall it was motivated by the definition of conditional probability, which was an exact motivation, an exact calculation of a certain probability in the discrete case. But in the continuous case, you're not really computing probabilities here because you have to integrate to get probabilities. But this formula still works. Use the joint density and divide by the marginal density for the given quantity Y. And this is an expression that will in general depend on both X and Y. And it does in this case, in fact. However, the way you think about it is important. You want to think of Y as fixed. And so you want to think of it as a function of X. And that was relevant on your exam when I kept asking you about the domain. In the double integral example, I kept asking you, what's the domain? What's the domain? What's the domain? And to play it safe, you could say the domain for both X and Y. But in reality, like for this one, you want to think about the domain in terms of X. Think of Y as fixed. The joint PDF was 1 over X. The marginal PDF for Y is this negative natural log of Y. And this simplifies to negative 1 over X natural log of Y, which you want to think of as a function of X. You want to think of Y as fixed. But it is a function of X whose domain also depends on Y. For that fixed value of Y, how does X vary? Just like before, it varies from Y to 1. The domain of this is between Y and 1. You want to think of Y as fixed, and so then that's, if that's the case, then that's a fixed number. That might be the trickiest part right there. The other one, the conditional PDF of Y given X, you want to think of as a function of Y. You want to imagine X to be fixed. The formula is similar. You still use the joint PDF on the top, but on the bottom, you use the marginal PDF of X, although that marginal PDF happens to be a constant. You're thinking of X as fixed here. So you're thinking of 1 over X as actually being a constant. The domain, just like this one depended on Y, the domain of this one does depend on X. Go back to the picture again. For any fixed value of X, how does Y vary? Along this vertical line, the second coordinate of that point is 0. The second coordinate of that point is X. Y goes between 0 and X. The domain is important. And that'll be relevant for finding the curves of regression. Continues to be confusing here with the domains. We want to find the curve of regression of X given Y. Is this a function of Y or is it a function of X? It's the mean of this variable. Leave some space there. To find it, I have to integrate that PDF times X, I guess, because the variable for this one is X. X times the conditional PDF of X given Y of X. How does X vary? X varies like this. From Y to 1 for any given Y. It varies from Y to 1. You're integrating out the X the x is going to go away, but you're still going to have something that involves y. This is a function of y. Like back and forth, right? With these variables. You really have to have the concepts clear in your mind. Now, when you do this integral, the x's are going to go away. But this formula still does have a y in it. So I will get a quantity that depends on y. Now, again, if y is constant, that would be a constant. But then at the end, you can say, hey, well, let me change y. Let me allow myself to change y. Think of y as a variable. Again, whether something's a constant or a variable is all in your head. But it's important to think of it one way or the other in various circumstances. If I multiply this x times this, the x's are going to cancel. I'm ultimately going to get the integral from y to 1 of negative 1 over natural log of y dx. Now that doesn't look easy until you realize, hey, y is a constant. So natural log of y is a constant, and negative 1 over natural log of y is a constant. I'm just integrating a constant there. So I get negative 1 over natural log of y times x. X goes from y to 1. And in the end, if you don't make a mistake in simplifying, looks like you should get y minus 1 over natural log of y. I did not make a mistake. Thinking about, if I ignore that negative sign, then the top will be at the opposite. But with the negative sign there, I switched it around. If I did not make a mistake, I'm not positive that I didn't make a mistake, then that should be the answer. We'll have Mathematica check it. And the other one, the curve of regression of y given x, is a function of x. Integrate the other conditional density. With respect to y. Based on this domain, y goes from 0 to x. So easy to get confused. I get confused too. I have to be very, very careful. And I'm still not guaranteeing I haven't made a mistake. There's your conditional PDF that you got to integrate with respect to y. I got to multiply times y. I get y over x. That's being integrated with respect to y. Treat the x as a constant, giving you y squared over 2x. Y goes from 0 to x. Looks like in the end, that's going to be x squared over 2x, which is just x over 2. Simpler. And maybe even intuitive when we look at the Mathematica simulation. That's halfway between 0 and x. Is that an accident? I don't think so. Let's confirm these answers with Mathematica here. So here I'm entering the marginal PDFs. This one was 1. On paper by hand, that's the same as this one. The other one says negative natural log of y, if condition, don't worry about the condition. Focus on the negative natural log of y, that's this one. I think the condition is that y is between 0 and 1. This does integrate to 1. Here I have some visualizations that I'm not going to bother talking about. Let's try to get to these curves of regression as fast as we can. What about these conditional PDFs? This is f sub capital X given little y. This is f sub capital Y given little x. What are their formulas? Did I get it right? 1 over x, that was this one. F sub y given little x. And the other one, yeah, that matches this. Mathematica is not telling us the domain unless maybe if I click this button, maybe it will. Okay, I'm not sure what it's doing there. You should realize the domain for this is x goes between y and 1. And the domain for this is that y goes between 0 and x. It was all based on the picture. I avoided the conditional expression by doing this. All right, let's confirm these curves of regression. Mu of y given x. That's supposed to be this one. This should simplify to x over 2. Let's see if it does. Yeah. And mu of y given x, that's this one down here, of x given y, excuse me. Hopefully, I did not make a mistake. Hopefully, it simplifies to that. Yep, if you put that negative sign up into the top, distribute it through, it'll simplify to this. Is it possible to think about these curves of regression intuitively? There's the curve of regression of y and x. The green dashed line is the top of the domain. This red line is the curve of regression of y given x. For any given x value, it's telling you the mean of the corresponding y values, which is halfway between 0 and x. Halfway between 0 and x. Does that make sense? That was a constant function. It's a uniform distribution. Constant between 0 and x. The mean is the midpoint. Midpoint of the interval is what I'm talking about, from 0 to x. X over 2. X is fixed. That's a constant function, a uniform distribution. Its mean is halfway between the endpoints, x over 2. And that's what's being graphed here. This is the graph of y equals x over 2. You need to imagine x as being fixed like 0.6 and thinking about what is the distribution along this vertical line. It's a horizontal line. It goes back to this graph being horizontal for any given value of x. I'm not saying this is easy, okay? If you're zoning out, you're probably completely zoned out, right? Like, I have no idea what he's talking about now. But if you sit down and concentrate, you can do it. Go through this example again. That's fairly simple, and the reason is because in the y direction for any fixed value of x, the distribution is simple, it's uniform. It's not so simple in the x direction for a fixed value of y. It's not constant, it's not uniform. And that's why the curve of regression for the other one is more complicated. Its plot is a curve. This can be confirmed with simulation. I'm not going to explain the simulation, but here I do have a simulation. I'm not explaining how I got it of this bivariate random variable. Do notice that the data certainly are most dense where the PDF is highest. And if you plot these curves of regression in here, they do make some intuitive sense. For any given value of x, like x equals 0.4, this straight line represents the mean of the y values. The distribution of the y values for any fixed value of x is fairly uniform. So the mean is halfway between the extremes. But for the other one, it's more complicated. For any fixed value of y, like 0.1, the mean of the x's is not halfway between the first coordinate of this point and 1. The data are denser in the x direction near smaller values of x. So you should expect the curve of regression to be closer to the left endpoint than to the right endpoint, which is what you see here.